Welcome to this explainer. Today, we're going to completely flip how you think about the word imperfection. Usually, when we call something flawed, we mean it's broken or maybe just less valuable, right? But today, we're diving headfirst into the fascinating world of materials science, where we'll see exactly why atomic flaws are actually the very features that make modern engineering possible.
Now, what if I told you that in material science, perfection is actually kind of a flaw? I know, it sounds totally counterintuitive. We just naturally assume that pure, perfect, crystalline structures are the ultimate goal. But a mathematically perfect crystal, one with absolutely zero irregularities, would actually be completely useful for almost everything we build today. It's the deliberate deviations from perfection that give metals their strength, let the semiconductors in our phones actually work, and make alloys so incredibly versatile.
To see what I mean, just take a look at this. You probably have one of these catalytic converters in your car's exhaust system right now. If you look closely at the atomic surface of that ceramic material, it's full of intentional defects. Those tiny missing atoms or stepped ledges, they're the exact spots where highly toxic exhaust gases like carbon monoxide get trapped. Because the atomic structure is literally imperfect right there, it creates this highly active site that bonds with the pollutants and breaks them down into harmless nitrogen and water. Without those very specific defects, the converter just wouldn't work at all.
Section 1. Zero-dimensional point defects, atomic mix-ups.
Starting at the absolute smallest scale, we have zero-dimensional point defects. These occur at just one or two atomic positions. The simplest one, it's called a vacancy. Think of it as an empty parking spot in an otherwise completely full atomic grid. Now, you might be wondering, couldn't you just cool a metal down enough or manufacture it so carefully that you eliminate all these vacancies? Well, according to the laws of thermodynamics, no way. The mere presence of these empty spaces actually increases the randomness or the entropy of the crystal, and nature absolutely loves entropy. In fact, just below the melting temperature of most metals, roughly 1 in every 10,000 atomic sites is completely empty.
On the flip side of a vacancy, we have the self-interstitial. This happens when an atom from the crystal jams itself into a tiny, normally empty void space right between the other atoms. Because atoms and metals are already packed in pretty tightly, squeezing a full-sized host atom into one of these tiny gaps causes a massive distortion in the surrounding lattice. It's exactly like trying to parallel park a massive SUV into a spot meant for a motorcycle. It just creates a lot of strain on all the neighbors. Because of that huge strain, self-interstitials are found in much lower concentrations than vacancies.
But what happens when the rogue atom isn't from the host material at all? When we intentionally add impurity atoms to a pure metal, we create what's called a solid solution. It's really just like mixing water and alcohol. They blend beautifully to form a single uniform phase. We can pull this off in two ways. Either a foreign atom swaps out a host atom directly, that's a substitutional impurity, or a small foreign atom just squeezes into the gaps, which is an interstitial impurity. And we do this on purpose all the time. Pure silver, for instance, is incredibly soft. But if we deliberately mix in some copper impurities, we create sterling silver, which is vastly stronger without losing that great corrosion resistance.
Now, you can't just smash any two random elements together and cross your fingers. For them to form a nice, stable, substitutional solid solution, they have to play by a strict set of guidelines known as the Hume-Rothery rules. First off, the two atoms must have a size difference of less than 15%. Otherwise, the crystal just gets way too distorted. Second, they need to naturally form the exact same crystal structure. Third, they should have similar electronegativities, because if one is way more electronegative, they'll just react and form a compound instead of a mixed solution. And finally, a metal is much more likely to dissolve another metal if it has a higher valency. When these rules align perfectly, like with copper and nickel, they can mix seamlessly in literally any proportion.
When engineers are in the lab actually designing these alloys, they need a reliable way to measure these deliberate impurities without getting totally bogged down in dense math. So they typically use two standard methods, weight percent and atom percent. Weight percent is super practical if you're on a manufacturing floor. It's just the mass of the impurity compared to the total mass. But if you really want to understand the material on a deeper chemical level, you use atom percent, which counts the actual physical number of foreign atoms. It's a subtle difference for sure, but absolutely crucial depending on whether you're pouring tons of steel or calculating nanoscale atomic strain.
Section 2. One-dimensional linear defects, shifting planes.
Okay, stepping up a dimension from individual single atoms, let's look at flaws that run along an entire line within the crystal. This is a classic example, an edge dislocation. Imagine taking a perfectly ordered block of atoms, slicing it right down the middle, and then just shoving an extra half plane of atoms into the cut. That line where the extra half plane ends, that's your dislocation line. The atoms right at that edge get severely squeezed together, while the ones below it are sort of pulled apart. These edge dislocations are a massive deal because their movement is the primary reason metals can bend and permanently deform, a process we call plastic deformation, instead of just shattering into pieces like glass.
Alternatively, if we apply a shear stress, think of twisting or sliding the top of the crystal relative to the bottom, we create what's known as a screw dislocation. Notice how, instead of an extra wedged half-plane, the atomic planes are shifted to form this continuous winding spiral ramp that twists all the way around the defect line. Now, in the real world, you rarely ever find just a pure edge or a pure screw dislocation. You mostly find mixed dislocations that sort of weave through the material, exhibiting a little bit of both.
Section 3. Two-dimensional interfacial defects, crystal boundaries. Scaling up yet again, we hit 2D interfacial defects. These are two-dimensional boundaries that separate completely different regions of a material. The most common one you'll see is a grain boundary. See, most solid materials aren't just one giant continuous crystal. They're actually made up of millions of tiny individual crystals, called grains, all jammed in together. Where these grains meet up, their crystallographic grids just don't line up perfectly. Because the atoms at these mismatched zones are bonded far less regularly, they sit in a much higher energy state, making them chemically way more reactive than the atoms safely tucked away inside the middle of the grain.
Another really fascinating 2D defect is the twin boundary. This one is highly symmetrical. When materials are subjected to severe mechanical shear forces, or maybe they're heated and cooled in very specific ways, the atomic lattice can effectively fold right over on itself. The result? The atoms on one side of this twin boundary take up positions that are an exact, perfect mirror image of the atoms on the other side. It's pretty incredible.
Section 4. Seeing and measuring defects. Okay, so these theoretical models are elegant and all, but how do we actually know they exist out there in the real world?
Well, for that, we rely on the absolute marvels of modern microscopy. This breaks down the big three techniques we use. For larger features, like those grains we just talked about, we use optical microscopy, which maxes out at about 2,000 times magnification using visible light. If we need to go deeper to see internal defects, we swap out light for an electron beam, zooming in 50,000 times or more. And if we want to get really crazy and map out literal individual atoms, we use scanning probe microscopy, which physically drags an incredibly sharp, nanoscale tip right over the surface to build a 3D topographical map. Want to see some proof? Take a look at this real-world transmission electron micrograph of a titanium alloy. We are magnified 50,000 times here. Do you see all those dark, tangled web-like lines crisscrossing everywhere? Those aren't artifacts or camera glitches. Those are actual physical 1D dislocations permanently captured on camera. It might look like chaotic structural damage, but that dense web of dislocations is exactly what dictates the immense strength of that titanium.
But what if we just have a standard optical microscope? Grain boundaries are so incredibly small, we can't just slap a piece of polished metal under a regular lens and expect to see them. So, engineers use a really clever trick called chemical etching. Remember earlier when we said grain boundaries are these high-energy, super-reactive zones? Well, if we apply a corrosive chemical to the polished metal, those boundaries will dissolve much faster than the inner parts of the grains. This carves out these tiny little surface grooves. When light hits those grooves, it scatters away from the lens, making the boundaries suddenly appear as dark, visible lines.
Once we can actually see these grains, we have to measure them, right? Because smaller average grain size usually equals a stronger material. We quantify this using a wonderfully straightforward procedure called the linear intercept method. It's highly logical. First, you take your scaled image and literally just draw random straight lines right across it. Then, you simply count how many times those lines cross over a grain boundary. Finally, you divide the total length of your lines by the number of intersections, adjust for your magnification, and boom, you have your measurement.
And here's exactly what that looks like in practice. By drawing these red lines, counting up the intersection points, and applying that intercept to math, we can mathematically determine the exact average size of these crystals. This is a huge deal. We are directly linking the microscopic, totally invisible world of atomic flaws to the macroscopic, measurable material properties that dictate whether a massive bridge stands strong or an airplane wing holds together in midair.
So, I really hope this explainer has completely busted the myth of perfection for you. Because in material science, perfection is basically just stagnant. It's the point defects, the linear dislocations, and the mismatched grain boundaries that actually allow us to forge stronger alloys, create faster electronics, and scrub toxic air from our environment. So I'll leave you with this thought.
If these precise, calculated flaws are the hidden secret to modern innovation, what ingenious imperfections will we engineer next?